Okay, let me switch over to my writing mode. Okay, wait, that's not what I want. Okay, wait, something's wrong. What's going on here? Okay, there we go. Okay, so today we're going to talk about the definite integral. So what did we talk about last time? We talked about, man, whenever I look at Zoom, I see Yusuf's profile picture, and it looks like he's like a person like video recording me. Does that make sense? Like I see him with the camera. It's sort of hilarious. I don't know if anyone else notices it, but he always shows up next to me on the screen when I click over, and it creeps me out. Like, oh my god, he's recording me. It's cool. It just looks hilarious though. I always do a double take when I see it. I'm like, what the hell is going on? Okay, so last time we learned about sigma notation. We talked about approximating the area under a curve with rectangles. Okay, so let's write that down. Draw and type. So last time we talked about approximating the area under f of x above the x-axis and between x equals a and x equals b. And we did this with rectangles. Let's just sort of like draw the picture. So here's like the x and y axis. And here's going to be our f of x. Oh wait, I think I'm not zoomed in enough. I need to zoom in more. There we go, that's nicer. Okay, so there's our f of x. So we want to be between x equals a and x equals b. So we're basically interested in this area here in green. Okay, we want to know approximately what's that area. So the way that we went about this was we drew some rectangles. Okay, so like I'll draw it as a left endpoint approximation. So the left endpoint of the rectangles will always touch the graph. And I'll try to draw them approximately the same width. That's not that bad, that's pretty close. Okay, so I've got my 4 rectangles. Rectangle 1, rectangle 2, rectangle 3, rectangle 4. Okay, so this area that we're approximating, we were adding up the areas of each of these rectangles. So remember we had like delta x was the width, and then the height was determined by f of x1. Right, so we had delta x, f of x2, plus delta x, f of x3, plus delta x, f of x4. Okay, right, so you have each of the rectangles, right, the area is going to be the width times the height. The width is always delta x, we have a formula for that, and then you choose some point, you plug it into the function, the f of x1 and f of x2, that's all that. Okay, so now instead of writing them all out like this, we had a quicker way to write it. So what do we use to write this in a more simpler format instead of having to write them all out literally? Honest question, not rhetorical. Yeah, sigma notation. So we would write sigma, and then we would write I equals, what's our first I value going to be? Given what I have written in the statement above. Yeah, I should be 1. And then what's the last I value going to be? 4, right? Because there's 4 rectangles. And then we have delta x times f of xi. Right? And with sigma notation, you take that I, you take I, you plug in 1, and then you plug in 2, you plug in 3, you plug in 4, and you get the line right above it. Okay, right? So it's a lot quicker to write this with sigma notation. Okay, so this formula right here, the sigma notation formula where we're adding up a bunch of rectangles like this, it actually has a special name. We call these Riemann sums. So if on the homework or in a book you see that it talks about a Riemann sum, all that is that it is a area approximation where you're adding up a bunch of rectangles. So Riemann sum is just this area approximation. So instead of saying like, oh, we're going to do an area approximation with rectangles, I'll just say, oh, this is a Riemann sum. Okay, now, why is this an approximation and not the actual area? Why is it an approximation? It's a good question. What goes wrong? Why is it not like perfectly the area that we want? Yeah, it's underestimated. So we're going to zoom in a little here, so you can see this a little better. Zoom in a little more. Oh my god, that was actually pretty good. I can just zoom in. So if you look, we're missing this area, right? Actually, this is an overestimation. You can see that it goes over the function. So the rectangles are bigger than they should be, right? Can everyone see where I like filled in the little green part? It goes over. Okay, so what we're going to talk about today is like, how do you get the actual area? Okay, this was an approximation. What can you do to literally figure out the real value of what that area is? So let's zoom out. Back to 300. So the question for today is, okay, why is it not letting me do it? There we go. How do you calculate the actual area and not just approximate it? Okay, that's our goal for today. Thank you. We want to get literally what it is. Yeah, so we're going to go through the process. It ends up involving infinite rectangles, but let's like build up to there. Okay, so let's scroll down just a little. Okay, too far, sorry. So let me draw an x and y axis. So if this is our function, so there's our f of x. I guess we could just zoom in. Okay, and we're approximating from x equals a to x equals b. Let's start off with two rectangles, left endpoints. So my first rectangle will look like this. My second rectangle will look like that. Okay, what is wrong with what I have so far with my area approximation? It is what? Too much. Yeah, it's too big. It overestimates. So what we can do is, let's see what happens if we go from 2 rectangles to 4 rectangles. So I'm going to split each of those rectangles in half. So I'm going to have this one end right here. Okay, wait, that's not working for me. Okay, I'm going to have that rectangle go right there, and then now this rectangle will go right there. Okay, before, we used to include this region right here. Right? Do you see that little green area? Right? By splitting that one rectangle into 2 rectangles, my estimate is better, yes? It's still not perfect, but does everyone see how it's better because I'm not including that green area now? Okay, I'm going to draw that for the other one. Let's erase that part. So I'm going to split it in half. It's going to look something like this. And once again, I'm no longer including this region right here. Okay, and I can keep doing that over and over. So as I keep on adding more rectangles, what's going to happen? So, oops. As we add rectangles, the amount of overestimate becomes smaller. In other words, the estimate becomes more accurate. Okay, as I keep on increasing the number of rectangles, I'm going to be adding less and less overestimate, which means slowly and slowly and slowly, I'm going to get closer to the true value. I'm going to pause for a moment. Are there questions about this idea? Can we see that from the picture that I drew is what I want to know. Cool. I can see nodding heads. Let's get some reacts in the chat or in reaction buttons. Also just want to see if people are paying attention. Okay. Cool, we got some people. So if the estimate becomes more accurate as you add more rectangles, what would the ideal situation be? So someone said this earlier. If more and more rectangles is more accurate, what should be your goal for the number of rectangles? Yeah, you want infinite rectangles. So let's scroll down. Let's zoom out. Let's go back to 300%. Okay, so if more rectangles is more accurate, then infinite rectangles should be perfect. It's like the best situation possible. Now, unfortunately, there's some issues with this. So if the number of rectangles is going to infinity, we're going to need to do some sort of limit calculation, right? N is going to infinity. That's what limits are for. Now, there's a problem with this. Delta x is defined to be b minus a over n. If n is going to infinity, what's going to happen to delta x? What will it go to? Yeah, it will go to 0. And why is that a problem for us? If delta x goes to 0, what else is going to go to 0? Yeah. I mean, 0 times anything will go to 0, but what is that? Where is that 0 going to show up? What other formula is it going to show up in? What do we use? Yeah, we use delta x in the area formula, right? We know that the area of each of those individual rectangles is delta x times f of xi, right? That's from the Riemann sum formula above, right? Remember, we have sigma delta x f of xi. So you sort of have an issue if you have the limit as n goes to infinity of the area formula. That's the same thing as the limit as n goes to infinity of delta x times f of xi, which means each of those individual areas is going to go to 0. So if your areas are 0 and you're adding up a bunch of areas, does that actually add up to anything? No, right? So you have this paradox. Supposedly it's becoming more accurate, but each of those individual rectangles, they're getting skinnier and skinnier and skinnier, and in fact the width of the rectangles is going to 0. A rectangle with no width has no area, and then there's nothing to add up anymore. So it's like, what the hell is going on here? Interestingly enough, you can use limits to step around this problem, right? That's what you spent in the first semester of calculus learning to do to deal with these paradoxical situations. Calculating limits allows you to sidestep these weird issues going on. Okay, so we're going to define the area under the curve as this. The area under the curve is going to be equal to the limit as n goes to infinity of the Riemann sum. So the Riemann sum here, so let's just look at the different parts here. The delta x f of xi, that's a rectangle. Now, this sigma part it tells you to add up the rectangles, yes? How many rectangles are you adding up according to the formula? Your I equals 1 and n on the top. So how many rectangles are you adding? Honest question. Yeah, n rectangles. So this is telling you add together n rectangles. Or add the areas of n rectangles. Which finally brings us to the limit. The limit is telling us, hey, instead of adding together n rectangles, how many rectangles would I like to eventually add? An infinite number of them, right? That limit of n goes to infinity says, go crazy, add together infinite number of rectangles. So this is basically telling us increase the number of rectangles to infinity. So this is how we're going to calculate that area. Boom! It's going to work for us. And we're going to do an example. So let's do an example using this formula to actually show that it works. Sorry, I have like a weird cough. So can I scroll down and do the example now? Or should I pause for a moment? I'm just going to ask if anyone needs me to stay. Cool, I'm going to move down then. So let's scroll down. So what we're going to do is we are going to use the definition above, because that's a definition, that's what we're defining the area as. We're going to use the definition above to calculate the area under f of x equals x negative x plus 3 between x equals 1 and x equals 4. So I'm going to draw what the picture of what this looks like. Let's put in an x and y axis. Boom, right there. Okay, my f of x is, negative x plus 3. So here's 1, 2, 3. It will hit right here at 0, 3. It will also intersect at 3, 0, right here. Okay, so let's draw on a line. So like there's our function. Boom. There's our f of x. Actually, let's change this. We're going to go from x equals 1 to x equals 2. My bad. Okay, so the area that we're interested in is between x equals 1. There's x equals 1 and x equals 2. So I'm going to highlight in green the area that we're interested in. Okay. Now, the reason so do you need calculus to calculate this area? That's a good question. No, because it's flat on the top, right? we're starting off with this so that we know what the area actually is, and I'm going to show to you that that definition we used above actually works. Does that sort of make sense? Like, we're going to start with something where like we know what the area is going to be. Let's see if that weird formula we had actually gives us the area that we're supposed to get. And it's actually not very hard to calculate this because you can split it up into two parts. There's this like square or rectangle-y part right here, and then there's this triangle right above it. So it's one tall and one wide. Actually, so let me change the color of how I do that. So you have this triangle part here, and then the rectangle, square part right down there. So the area of my region is 1 for the square part. Sorry, someone like called me. I'm gonna put myself on Do Not Disturb. There we go. So you have 1 on the bottom, and then you get the area of the rectangle above is 1/2. So we know that the area is 3/2. Okay, so when we do that calculation, the limit of the Riemann sum, we should get 3/2. Cool. Okay, so let's show you how this will go down. So let's start with that definition. We're going to have the limit as n goes to infinity of sigma I equals 1 to n of delta x times f of xi. Okay, so I'm just starting off with the definition, the one that I gave you earlier. Okay, so now we have to like start plugging in the pieces. So you work like how you normally would in math, like from inside out. So we're gonna start with calculating delta x. We'll do that right here. So we know that by definition, delta x is b minus a over n. Our b and our a in this case are 2 and 1. So the b is 2, the a is 1, 2 minus 1 is 1. So you get 1 over n. You don't plug in a value for n because we're going to be taking the limit as n goes to infinity, so you need the n in there. You can't plug in like n equals 5 right now, because that would mean that you're dealing with 5 rectangles. You need to leave the variable so you can let the number of rectangles go to infinity. So leave variable so n can go to infinity. Does that make sense to everyone why you can't just plug in a value of n? Because like from the previous examples, right, we always had a value of n. For this you won't. Okay. Now we need to plug in this. Okay. So remember your f of x is negative x plus 3. So your f of xi is negative xi plus 3. And you have to remember from the previous examples, do you remember how you would plug in all those different values, the left endpoints of the rectangle? There's a nice formula for this. The formula for the left endpoints of the rectangle, it's a arithmetic progression. So what it's going to be is, there's a formula is a plus delta x times I. So in this case, our a is 1. Our delta x is 1 over n. And then the I is I. So this formula is always the same no matter what. If you're using a left endpoint at least. For our purposes, you can just always leave it like that. Okay, so now you're going to plug that in. Let's put a little line right here. So you get let's multiply the 1 over n and the I together, so you get I over n plus 3. That's your f of xi. Okay, so we're going to have to take all these pieces and plug them into our formula. So I'm going to do that right here. We have the limit as n goes to infinity of sigma I equals 1 to n. Now delta x we will replace with 1 over n. And f of x we will replace with this stuff that we just calculated, which is, let's distribute this negative. So we're going to get minus 1 minus I over n plus 3. So all I did there was I took my delta x, which I calculated, I took my f of xi, which I've just calculated in blue and red, and I plugged it into the formula, which was in white. So I'm just going to pause because I know that people are going to be writing for a moment. So I'll give you a moment to write that down and think about it. Okay. So now we're going to have to just start, what's it called? Simplifying my expression here. So let's work on that. So I'm going to scroll down a little. Let's start with simplifying the stuff in here. So the negative 1 and the 3 will go together, which will give us 2. So you get 2 minus I over n. And then you have the 1 over n out in front. And then you still have all that, the sigma and the limit. Let's just simplify the inside before I keep writing those. So actually, let's just move this over to here. I'm going to lasso it. This is like so amazing. I love technology for this reason. I could just like move this over. So over here, we'll just have like a little line saying that we're simplifying. And then we'll go back and write the limit and the sigma and all that. Okay, so let's distribute the 1 over n. So if you distribute the 1 over n, you're going to get 2 over n minus I over n squared. Okay, so now you can rewrite this. You have the limit as n goes to infinity of sigma I equals 1 to n of the expression you're dealing with is 2 over n minus I over n squared. All right, that just came from my calculation over there. So I use this to go back to right there. And now we're going to be able to use the material that we discussed yesterday. Notice that I have the sigma of a difference. Whenever you have a difference in the expression of the sigma, what can you do to that? Yeah, you can split them up, exactly. So we're going to do that. Scroll down a little. So I'm going to get the limit as n goes to infinity, and I'm going to put brackets around it so you can see how it's being split up. The limit's applying to everything. I'm going to get two sigmas now. I have the sigma of I equals 1 to n of 2 over n minus a sigma I equals 1 to n of I over n squared. Okay, so we use the sigma rule and we split it up. And there's actually more that we can do now. And you have to be very careful about what the variables are. So what is my variable for the sigma? So the sigma, remember there's always the index of summation or the variable of summation. What is the variable for the sigmas? So you have a 50-50 chance of guessing properly. It's I, right? The variable is always the variable you see here at the bottom, which means the n is a constant as far as we are concerned. N is a constant as far as the sigma is concerned. Which means that we can actually factor it out. Or we could use the constant rule. Oh, okay, one second. I need to plug in my little writing tablet. It's dying. So I just need to quickly get the charger for it. Plug it in. No, I don't have enough ports on my computer. Okay, I'll just unplug my mouse since I can use it as a mouse. Come on. Come on, plug in. You can do it. Yeah, there we go. I'm good now. Okay, so let's keep going forward. Okay, so what here for the sigma 2 over n, the 2 over n is a constant. What is the formula you can use? If you have sigma I equals 1 to n of some constant k, what was the formula that we had for that? What can you turn that into? Do you remember? Do you remember? It's something times k, something times the constant. Yeah, so you take the top, which is n, you subtract the bottom, which is 1, and then you add 1, and then you times by the constant. Notice if the negative 1 and the positive 1s cancel, so you get n times k. Which means this sigma 2 over n is going to be n times 2 over n. Boom. Okay, now there's a little more work. We have to work on the other sigma. Let's do that in blue. So we have sigma I equals 1 to n of I over n squared. That n squared on the bottom of it, that's a constant, so you can factor it out. So you can get 1 over n squared sigma I equals 1 to n of I. And we have a formula for sigma. Does anyone hear that? Is someone talking in the background? Okay, I'm just gonna find them. Yeah, someone's unmuted. There we go. I think we got it. Cool. Oh my god, earlier today, someone Zoom bombed me and they logged in as my name. It was sort of cool actually. I don't know why they would do that though. It means that they were in the class, or someone in the class gave it out and gave them my name. They were like spamming things in the chat. So anyways, back to here. What is the formula for sigma I? So we have that 1 over n squared. What's the formula for this part? The sigma I. Yeah, the n times n plus 1. It's n times n plus 1. Pretty close. N times n plus 1 over 2. So that second sigma becomes 1 over n, n times n plus 1 over 2. Let's put the brackets around it. And then now we have our limit as n goes to infinity. Boom. So now it's just algebra. We just need to, and taking the limit, so we'll just, focus on that for a moment here. So I'm going to scroll down a little so we can do that. Okay. So we're going to have the limit as n goes to infinity. Okay, this n and that n cancel, so we get a 2. Minus, okay, let's multiply this out on the top. We get an n squared plus n over 2n. I screwed up somewhere. Oh, yeah, this is supposed to be an n. This is supposed to be 2n squared. I forgot the square right here. There we go. Thank you for catching that, Siddhartha. Okay, so what's obviously the limit of 2 going to be? Let's do the easy part first. You can use the limit rules to break this up, right? So what's the limit of 2 going to be? 2, yeah. And then minus, so now you're taking the limit of n squared plus n over 2n squared. Does anyone remember how you calculate limits as something goes to infinity when you have powers on top and powers on bottom? How does that work? Do you remember how it works? Like if you have the limit as n goes to infinity of a n squared over b n squared, what is that going to be? Yeah, cool. Which means we look at the ratio of the coefficients of the highest powers, so you get 2 minus 1/2, and then oh my god, what is 2 minus 1/2? The 3 halves that we said we were going to get earlier in the video. If you were to scroll, if I scroll back up, we would see that the area we were expecting to get was 3 halves, right? So it gives us exactly what we were expecting. Boom. Okay, so it works. Okay, so I guess the big takeaway here is that, oh my god, that crazy formula works. Okay, so that's really, we're not going to use this formula all that often because it works, but what's the issue with all this? Like, why would you not want to do this very often? Like, it's super long to do this. Like, you have to take a limit, you have to do sigma calculations. Like, this takes forever. Like, nobody has time for this, if we were to reference a very popular meme. I think her name was Sweet Brown or something like that. Does everyone know what I'm talking about? That ain't nobody have time for that meme? Yeah, I mean, this would take forever. Okay, so we're going to come up with better ways to do this. Okay, that's what we're going to talk about after this. Okay, so this area calculation that we just did, it's called a definite integral. Okay, so it's the area under f of x above the x-axis between x equals a and x equals b. That's what we just calculated, right? And the way that we write this is the limit as n goes to infinity of sigma I equals 1 to n delta x times f of xi. We call this the definite integral. It's a pain to do the calculations. And we have a shorthand way of writing this. We use something called the integral symbol. It looks like a long S. And you put A and B on the top and the bottom. Those A's and those B's, the A and the B there refers to being between A and B. And then in front of it, you put the function. Oops, it's not letting me write. What the heck? You put the function that you want the area under. And then finally, you put a dx. So if you see this, it's telling you, hey, find the area under f of x between A and B. We call that the definite integral. This dx here, it functions a lot like how when you take the derivative, you can take the derivative with respect to something. Like, do you remember here on the bottom, this is the derivative of y with respect to the variable x? This dx over here works the same way. We say that we're integrating with respect to x. So the dx doesn't like do anything, it's there as notation. Okay, so you're always gonna see that there, but it's never gonna like, you're never gonna do anything with it, I guess is the point here. Okay. Bueno so far? Okay. So we use some things interchangeably. Integrating, let's write this. Okay, it's not letting me type. I want to type. Okay, why is it not letting me? Okay, I'll scroll down a little. Come on, move down. There we go. Okay, I want to type down there. Thank you, finally. Integrating is, as far as we're concerned right now, the same as finding the area under a curve. Oops, I didn't spell finding right. So just know that I'm going to use those interchangeably for a little while. I might say, oh, let's integrate this. Really what I mean is we're finding the area under the curve using this definite integral definition. Okay. How are we doing on time? What time are we going until? Okay, cool, we got like 10 minutes, thank you. 10, 12 minutes. Okay, so unfortunately this doesn't always work. You can't always find the area under a curve. There's like weird examples that you can come up with that like things that have no area. So like, let's write that down. So there are functions which have no area under them. They're really weird. We won't discuss them in this class, but they exist. Just want to tell you about them. As long as your function is continuous, it will have area under it. In other words, it is called integrable. So this is like important vocabulary. If integrable. Okay. And as long as you're continuous, you do have area under the curve. So everything that we're going to be dealing with will be continuous. Okay. Some other stuff that we're going to talk about. So when we talk about area, we are dealing with what is called signed area. So let's take a moment to explain what that means. So let me draw a x and y axis here. Okay, so there's my x and y axis. Let's say you have a function that looks like this. Oh, whoa, okay, that's not what I wanted. There we go. Oh, I wanted blue. Okay, there we go. Let's say that's your function, f of x. And let's say that x equals a is right here. And let's say that x equals b is over here. So if I write the integral a to b f of x dx, I'm interested in finding this area in green. I'm like putting little tick marks right here. Okay. So there's actually a difference between the area up here on the left-hand side and the area down here on the right-hand side, which is alternatively above and below the x-axis. The stuff on the left up here, it has what is called positive area, whereas the stuff down here has negative area. And just like positive and negative numbers, positive and negative areas can cancel out. So let's say on the left, I'm just making this up, let's say that the area on the left has an area of positive 5. And let's say that the area on the right has an area of negative 5. We're interested in what's called the net signed area. The net signed area means that you add together the positives and the negatives, and what you get is whatever's left over after they cancel. So in this case, what would my integral be equal to? Because you have a positive 5 area on the left and a negative 5 area on the right. Yeah, you'd get 0. So that sort of like upsets people a little, but you just have to remember that the positives and the negatives can cancel, and you're interested in the net area. Okay. So you can sometimes get 0 even though obviously it looks like there's an area there, because we're interested in the net signed area. Okay. Any questions with that idea? It's usually, I think it's sort of straightforward, but if there are any questions about it, I'm willing to entertain them. Looks like most people are good. Okay, let's talk about some other stuff about this. Okay, so the net signed area is different than the total area. Okay, come on, let me type. What the hell? Total. So what is total area? So the total area is what you get if you disregard the fact that the areas can be signed. In other words, positive or negative. Okay, and if you're interested in this, what you need to write is a, b, absolute value f of x dx. So because you're taking the absolute value of the function, what happens to the part of the function that was below the x-axis over here that I'm circling in red? The person who messaged me for the net signed area, you just add up the positive area and the negative area, and whatever you get, you add them, you don't subtract them. But back to what I was talking about right here, because you're taking the absolute value of the function, what happens to this area that I circled that was negative? Yeah, it becomes positive, so it would be reflected over. So this area, which used to be a negative area, would become a positive area. And for this example, you would get 10. Right? Because you get the positive 10 on the left, the positive 5 on the left, and the positive 5 on the right. So usually people, when they think of area, they think of total area. So you have to be careful about which one you're talking about. Okay, so does that make sense, the difference between the net signed area and the total area? You know that you need to calculate the total area if you have the absolute values around your function. forward. Let's talk more about this. Scroll down. So let's talk about some of the properties of the integral. The definite integral. Let's turn that into a... Oops. Sorry, I'm having difficulty. There we go. I just want to make it big. Okay. Yes. Scroll down. So let's say that you're integrating from some number a to some number a, f of x dx. Now before we say what this is equal to, let's draw the picture. So we have our x and y axis, and we have our function, f of x. So obviously we want the area under f of x and above the x-axis, but how else do you need to describe it? It's between what and what? Between a and a, which means how wide is the area that you're calculating? Yeah, the width of the area that you're calculating is 0 because, you know, your limits of integration, they're called, are the same. Let's write that down here. These numbers here are called the limits of integration. If your limits of integration are the same, you're trying to calculate the area of something which has 0 width. So if you're dealing with something that has 0 width, what should your area be? 0. Boom. And this is only true if f of x is defined at f of a. Otherwise, your integral will be undefined. So basically, if your limits of integration are the same, you're going to get 0 for your integral and your area. Okay. Since we only have like a minute or two left, I think this is a good time to end the recording. We'll just pick up here tomorrow. So I'm just going to stop the recording.